Good afternoon, dear students. We are going to continue with isotope tracer technique. In the last presentation, we discussed about radioactivity. Okay, what are the units of radioactivity and what is the effect of radiation on a molecule? When a molecule or an atom is exposed to radiation, it may undergo ionization or excitation. The ionization or excitation radiations can be measured, okay, by using various type of counters like say Geiger-Müller counters, scintillation counters, etc. Okay, Geiger-Müller counters are generally used for ionizing radiations. Okay, ionization to study the ionization. Right. Now, Geiger-Müller counter actually operates beyond the region of ionization chamber and proportional chamber that we have discussed. Right. Now, what is a Geiger-Müller counter? It's a device used for detecting and measurement of all type of radiation, especially alpha, beta and gamma, especially alpha radiation. Okay. Now, the Geiger-Müller counter consists of a tube and a counter and power supply. Okay, the Geiger-Müller tube is usually cylindrical with a wire down the center. The counter and the power supply has voltage controls and time options. A high voltage is established across the cylinder and the wire, where cylinder serves as cathode and the wire serves as anode. So a potential difference is applied and a large voltage current is generated. Okay. Now, what happens? See, when any ionizing radiation like alpha, beta or gamma enter inside the tube, through the mica window, it ionizes the gas molecules. Upon ionization, electrons are knocked out of the atom and the atom becomes positively charged. So, the positively charged molecule entity moves towards negative electrode and electrons move towards positive electrode. Okay, and the circuit gets completed. The electrons that are knocked out of the atom are attracted by the positive electrode and positive charge ions are attracted to negative electrode. And when the current is this completes the circuit, a pulse of current is generated which is detected. After the pulse is counted, the charged ions becomes neutralized and the Geiger counter is ready to record another pulse. The most important thing in Geiger counter is one must have appropriate high voltage across the electrode. If the voltage goes down, pulse also cannot be detected, and if the voltage becomes too high, it may damage the tube. So this we all discussed in the last presentation. Now let us discuss about the disadvantages of using a Geiger-Müller counter. Number 1, high voltage is required. Number 2, the the counter has inability to distinguish between pulses. It cannot distinguish between alpha or beta particle because their pulse is similar. They produce similar pulses. So the counter cannot distinguish. Now, some time is required for ion pair to reach their respective electrodes. As soon as a gas molecule becomes ionized, ions are formed, positive and negative. They require certain time to reach the electrode. During this time, other particle entering inside the tube does not produce ionization and hence can go undetected. Okay, and it can escape. This time required in a GM tube is called as dead time of Geiger-Müller counter. It may be of 100 to 200 microseconds. Even some of the ion escape to reach the electrode and produce their own ionization avalanche. Due to this, continuous discharge occurs. Okay, so during the dead time in a Geiger-Müller counter, there is no ionization. Molecule can go undetected. They can escape and produce their own ionization avalanche. So continuous discharge can occur. This has to be overcome. This can be overcome by adding quenching agents like ethanol, gas of ethanol, ethyl formate, halogens, etc. Okay. Now, generally, the tube is filled with inert gas like helium or neon or argon, having small amount of quenching agent. Okay, quenching agent may be butane or propane or ethanol, ethyl formate, chlorine, bromine, etc. So, to avoid the continuous discharge, quenching agents are mixed with the gas that is filled in the Geiger tube. These quenching agents prevent continuous ionization. Okay, they prevent continuous ionization and if not prevented, detector will not respond to any other particle, the very first particle which enters the other than the first particle. Okay, so these quenching agents actually are added to the inert gas present in the tube to prevent continuous ionization, so that during dead time in the Geiger counter no ionization takes place. Okay, because of all these events, the quenching agent is utilized, and each quenching agent results in the destruction of the quencher. The Geiger tube, therefore, should become useless after some time. When the quenching agent is slowly destroyed, and if it is exhausted, the Geiger tube may become useless after some time, say after 10 raised to 8 to 10 raised to 10 pulses. Okay, so the above limitation of conventional tube is addressed by using a flow tube. Okay, so initially we use a flow tube, right, to avoid this problem. Such a tube, the flow tube, has entrance and exit port through which gas is made to flow continuously. Okay, what do we use? We use a flow tube where there is entrance and exit port. The gas is made to flow continuously. Even here the window is eliminated. Okay, why? To allow measurement of beta particles which have very low energy and cannot even enter a thin window. Okay, beta particles having low energy cannot even enter a thin window, and hence these flow tubes do not have any window. This modification is known as windowless flow counter, and it will help in getting better results, right? Or it will help in increasing the time of pulse detection of pulses, right? All these you can say difficulties can be overcome. So Geiger tubes are not too much used because Geiger tubes have been now replaced by scintillation counters, but still in some experiments we do prefer using a Geiger-Müller counter. They are operated at 1100 to 1400 volts, which may differ from tube to tube. The tube should never be allowed to operate in continuous discharge region because it can damage the tube. Okay, so these are the disadvantages of Geiger-Müller counter. Now, there are certain practical aspects also of Geiger tubes which are to be taken care of. Number one is background count. A Geiger counter operated even in the absence of a radioactive sample will register some count. This is known as background count. Okay, if you are using a Geiger-Müller counter and there is no radioactive sample, still some pulse is generated or counts are registered by the counter. These are called as background count. Why this type of count take place, background count occurs? This may be due to any naturally radioactive substance present in the vicinity of the counter, nearby X-ray source or cosmic rays, right? The background counts are created due to the presence of natural radioactivity in the vicinity of the counter or X-ray sources or cosmic rays. The background radiation can be reduced by shielding the instrument with lead. The instrument can be shielded with lead so that surrounding radiations are not counted. However, the value of background count must always be subtracted from the actual count. You have to subtract the value of the background count. Okay, or you can shield your instrument by lead. Number two, second practical aspect is geometric effect. Now see, generally steel planchets or ground glass disc are used for drying the solid samples before they are counted, and with a thin end window tube. Okay, so before counting, you have to dry the sample, right? Such samples, you have to place the samples in more or less the same positions, and all samples must have same surface area. Okay, all the samples should be placed in the same position with respect to the counter and they should have same surface area. Otherwise, the fraction of the emitted radiation entering the tube may vary and may cause large errors. Okay, so the orientation of the sample, the position of the sample should be similar each time when you are counting. Otherwise, it will cause error. The geometric effects are higher for soft beta emitters. Okay, these geometric effect, the position of the sample may cause serious or large errors as well as soft beta emitters are concerned. Thus, if the position of soft beta emitting isotopes like C14 or S35 varies by just 1 millimeter, the count may vary as much as by 5%. Okay. So, you have to take care that the position of the isotope remains same every time. Okay. For high energy emitters like P32, geometric effect may not be a significant factor. Okay. Now the self-absorption. If the sample that you have prepared is quite thick, if the sample is not thin, it is very thick, then radioactivity from its center, the radioactivity from the center of the sample will have to travel or traverse the solid above it, then the air, and then the window before it enters the tube. That means it has to traverse a great distance. In such cases, particles emitted out from the center of the sample are absorbed by the sample itself and they never reach the counter. So if your sample is thick, then particles emitted from the center of the sample will be absorbed by the sample itself and they will not reach the counter. This is so mostly with beta emitters like C14. This is known as self-absorption and the sample is known to be infinitely thick. And hence, how it can be corrected? Self-absorption can be corrected only by using thin samples as possible and infinitely thin samples as possible. However, it is best to measure beta emitters by scintillation counting. Okay, beta emitters cannot be efficiently measured by GM counter because of self-absorption problem, or you can say because of geometric effect, and hence they are best measured by scintillation counters. So let us now discuss scintillation counters. Okay, scintillation counters we will discuss in our next presentation.